Hi, my name is Shruti and this is my video submission for assignment 2 part 2 of Info 6105 Data Science Engineering Methods. The first question that was given to us was to derive the ELBO from the KL divergence between approximate posterior Q of z given x and true posterior P of z given x. Show explicitly how maximizing the ELBO will minimize this divergence. So the way I have understood this question is that we are trying to approximate the true posterior P of z given x, which we can't compute exactly. So we introduce a much simpler distribution Q of z given x and measure how close it is to the real one using KL divergence. When I expanded the KL using the Bayes rule, I rewrote P of z given x in terms of P of x and z. After simplifying it, it gives the result of log P of x is equal to ELBO plus KL divergence between Q and P. This shows us that the ELBO is a lower bound on the log likelihood of data. So if we maximize the ELBO, we're actually minimizing the KL divergence. That pushes our approximate posterior closer to the real one. That's exactly what the VAEs do. They optimize the ELBO to learn meaningful latent representation. The second question that was given to us in the assignment was to derive and interpret the analytical KL divergence between two multivariate Gaussian distributions. So in this question, we are comparing two multivariate Gaussian distribution Q and Z and P and Z. KL divergence tells us how different they are. Since they both are Gaussian, they are very close, the solutions are very close to each other. I started with the KL definition, plugged in the Gaussian formula and simplified it. The final result has a total of 4 terms. One for the volume ratio, one on how the shapes differ from one another, one is how far the means are from one another, and one is to adjust the dimension. So basically, if the mean and the covariant are far apart, then the KL increases. In VAEs, this KL is what we minimize to keep our learning distribution close to the prior, which helps structure the latent space properly. In the third question, we were asked to discuss the implication of the KL divergence term in the ELBO as a regularizer. What happens if it's omitted during training? The KL term in the ELBO acts like a regularizer. It basically will stop the encoder from memorizing too much or learning overly specific about the input. Instead, it will encourage the encoder's output to be a distribution of z for a given x, because of which the model will learn a smooth and a structured latent space where points that are close to each other, once decoded, will actually make sense. Now, if we remove the KL term, the model will turn into a basic autoencoder. It might just, it will still reconstruct things well, but the latent space will get too messy and it's no good for generating new data, which means that the KL term is really important if we want the model to actually be generative and not just to compress information. The fourth question, we were asked to explain mathematically and intuitively why GAN training can suffer from mode collapse and to propose a solution to discuss their mathematical reasoning. So in this question, mode collapse happens when GAN's generator starts to produce the same few outputs repeatedly, even though the real data is diverse. What's happening here is that the generator finds a way to fool the discriminator with certain samples and just stick to them. Mathematically, this happens because the generator is minimizing log of 1 minus the discriminator's output for generating few samples. If the discriminator gets too strong, the gradient will push the generator towards only a few outputs. To fix this, we can use feature matching, which is where the generator will match internal features instead of just trying to fool discriminator. We can also use mini batch discriminator or Vastein's GANs, which will help smoothing the gradient and better diversity. The main goal is to get the generator to care about variety and not just realism. In the fifth question, we were asked to explain how a VAE can suffer from posterior collapse and discuss mathematically and practical strategies to address it. In VAEs, posterior collapse is when the decoder stops using the input and just outputs something close to the prior. like standard normal. That means that the latent variable z does not carry any useful information and the decoder ends up doing everything. It usually happens when the decoder is too strong and can reconstruct x even from a random z. So the optimizer just minimizes the KL term by collapsing Q of z for a given x to match P of z. To avoid this, we can use KL annealing, where we increase the KL weight gradually, or we can also use the beta VAEs to reduce KL pressure. There are other fixes as well that include lagging encoder updates or using a weaker decoder that forces to rely on Z. These strategies help ensure that the encoder actually learns meaningful latent features.